Hello, good morning.
Good morning, sir.
So, yesterday somebody has requested me to repeat the topic of self inductance and mutual inductance. So, let us discuss this further. So, this is how magnetic flux can be expressed in integral form. Magnetic flux is magnetic lines of force. It is the magnetic uh, induction into area. Okay, because magnetic field can be defined as the magnetic flux per unit area. So therefore flux is equal to B into A is the area. So magnetic flux, B is the magnetic field, A is the area, and theta is the angle at which magnetic field lines pass through the given surface area. So this is what we have seen. So these are the diagrams which can explain you. The magnetic field also can be defined as the force per unit current per unit length of the conductor. Okay, so that is its SI unit will be Tesla, that is kg per second square per ampere. These diagrams are very clear how magnetic flux is related with the lines of force. Okay, so Faraday's laws of electromagnetic induction, where the magnetic flux, if it is linked with a coil, then the EMF will be induced in the coil if that flux linked with the coil will change. So rate of change of flux induces EMF, and that induced EMF is directly proportional to d phi by dt, that is rate of change of flux, and that will reduce the rate of change of flux. That means that will oppose the motion of the magnet. So this is combinedly known as the Faraday-Lenz law. Then yes, it can also be expressed mathematically as phi is equal to, as we know, it is double integration of B dot ds. So if you put that value of phi, then the expression will be like this. So this is, we can say, integral form of Faraday's law. Similarly, one can express that in a differential form. So from the electrostatics, EMF is equal to line integral of E dot dl. So applying the Stokes law, we can express that it as curl of E is equal to minus dB by dt. So curl of E is equal to minus dB by dt is the differential form of Faraday's law. Then self-induction. Self-induction means, so when we apply the EMF to the coil, or say when you start the current through the coil slowly. So when the current through this coil changes, so current will flow like this. Current will flow like this. Current means charges are flowing like this, and the rate of flow of charge is there because initially the current starts from zero and it reaches the maximum value. So there is a change in current. Okay. So due to the change in current, the magnetic flux linked with coil, because change in current produces magnetic field, and due to change in current, the magnetic flux will change, and that change in flux will produces EMF, which opposes this change of current. Okay, is that clear? So due to change in flux, there is a EMF induced in the coil. That induced EMF will oppose the change in current. So this phenomena is called the self-induction. So change in flux is directly proportional to the change in current. Phi is equal to L into I. L is a proportionality constant which is called the self-induction. E is equal to minus d phi by dt. Therefore, E is equal to minus L di by dt. And therefore, L can be expressed as E is equal to L is equal to minus E upon di by dt. So L is a self-inductance of a particular coil which is equal to the EMF induced per unit rate of change of current. If there is a unit rate of change of current, then the EMF induced will be equal to self-inductance. And its SI unit is Henry. Similarly, one can get the mutual induction. Now here there are two coils. Okay. So this is one coil which we have seen as earlier. The voltage source is applied to this coil. So there is a change in current in this coil. Okay. And the magnetic flux is linked with this coil 1. And this is the coil 2 which is near the coil 1. So that these magnetic lines of force are also passing through this coil 2. Okay. But there is no source of EMF here. There is a source of EMF here to produce the change of current. But here there is no source of EMF in coil number 2. Now, due to change in current, change in flux, okay. Now, the flux will change due to the change in current in coil number 1. Okay. If current I1 is changing, the flux will change, which is linked with coil number 1. And the same flux will change, which is linked with coil number 2. So due to rate of change of flux in coil number 2, EMF will be induced, and that will be E2. So E2 is the EMF induced in coil 2 due to rate of change of current in coil number 1. Okay, so this is the mutual induction. So EMF is induced in coil number 1 also due to rate of change of flux. But here, because of the mutual induction, there is a EMF induced in coil number 2 because of rate of change of in coil number 1. So this is called the mutual induction. This is the property of the two coils kept together. So when current flow through the coil 1 changes, magnetic flux linked with coil 1 changes, and the magnetic flux linked with coil 2 changes, and EMF induced in coil number 2, and which opposes the, of course, change in flux. So EMF induced is equal to this much. So this is called the mutual induction. Coil number 1. Yes. So this phenomena of mutual induction is used in the transformer. Okay. So transformer is the electrical device which converts high voltage into low voltage, or say low voltage into high voltage. तो ये सब रिपीटेशन हो गया है. If anything you want to have repetition during the lecture, you can tell me. This is what we have seen. I have shared my videos and PPTs. If you still want any material, you can ask me. Losses, ये important है. Copper losses, eddy current losses, magnetic flux leakage, hysteresis loss. Condition of ideal transformer: primary and secondary coil should be negligible. Resistance should be negligible. Self and mutual inductance of primary and second coil should be very high. And there should be no magnetic flux leakage, and there should be no energy losses. So there are several uses of transformer. So these are the numerical problems we have already discussed. Simple problems are there so that you can calculate the parameters, like say primary current, primary voltage, secondary voltage, transformer ratio, or say turn ratio. These parameters can be easily calculated by using the simple formula. So this is another problem.